For nearly a century, cosmology has relied on an elegant framework called the Standard Model. It is a set of equations that has explained the history of the universe with almost suspicious precision. This model acts as a rigorous architectural blueprint. It dictates the exact speed of cosmic expansion, the specific era when galaxies are allowed to form, and the internal physics required for stars to ignite. Humanity spent decades building the James Webb Space Telescope for a singular purpose: to observe the early universe and provide the final, definitive confirmation of these mathematical rules. If the data Webb collects deviates from this model, our entire timeline of cosmic history loses its foundation. Once Webb moved beyond the thermal interference of our atmosphere, it began looking further back into the darkness than any instrument in history. Physicist Adam Riess, a man who has spent his career measuring the expansion of the cosmos, looked at the resulting data and arrived at a stark conclusion: we have misunderstood the universe. This assessment comes from a Nobel Prize winner reading data that simply does not add up within our current model of reality. Webb's initial surveys have identified direct contradictions to 4 established principles of physics, creating a crisis that spans from the birth of the first stars to the expansion of space itself. The first conflict concerns the expansion of space. By analyzing the faint afterglow of the Big Bang, the Planck satellite predicted that the universe should be expanding at 67 kilometers per second per megaparsec. Webb tested this by looking at the present-day universe instead of the past. It measured the distance to pulsating stars called Cepheid variables to calculate the expansion rate happening right now. Webb returned a value of 73. In a field where measurements are routinely accurate to within 1%, an 8 or 9% gap is enormous. It suggests the universe is expanding significantly faster than our best theories allow. Scientists initially hoped this tension was a simple measurement error caused by Hubble's cameras blending the light of nearby stars. However, Webb's superior infrared vision confirmed the higher expansion rate with near-perfect precision, ruling out the possibility of a mistake. Because everything in cosmology depends on this expansion rate, this single discrepancy suggests the universe could be over 1 billion years younger than we previously calculated. Our second established rule is that every star is powered by the nuclear fusion of hydrogen in its core. Webb challenged this when it spotted a massive object, Jade's GS-Z40, existing a mere 300 million years after the Big Bang. According to the Standard Model, the universe at this age should only contain small, dim, infant structures. Instead, Jade's is an impossibly bright, compact object holding millions of suns worth of matter. It lacks the internal conditions required to trigger fusion, yet it radiates an immense amount of energy. This cross-section shows the only theoretical explanation that fits the data: a dark star. In this model, dark matter particles gathered in the core collide and annihilate each other. This reaction generates the outward pressure needed to keep a massive cloud of hydrogen glowing without ever needing fusion. If dark matter can actively fuel these massive stars, we have to revise our understanding of it as a passive, invisible scaffold and instead view it as an active driver of early cosmic history. Rule 3 defines a speed limit for black hole growth, called the Eddington limit. As a black hole consumes matter, it releases intense radiation that pushes away any remaining food, forcing these objects to grow slowly over billions of years. Webb discovered hundreds of little red dots existing just 600 million years after the Big Bang. They initially appeared to be galaxies holding far more stars than the early universe should have been able to produce. When Webb analyzed the light from these dots, it found hydrogen gas orbiting the centers at 3.2 million kilometers per hour. That velocity requires the extreme gravity of supermassive black holes, objects that simply hadn't had enough time to grow that large. These black holes likely bypassed the star formation phase entirely through direct collapse, where massive clouds of gas fell inward to create a giant black hole seed in a single step, slowing down for impact. This discovery inverts the expected order of cosmic growth. These black holes reached gargantuan proportions, while their host galaxies were still in their earliest stages of assembly. Rule 4 concerns gravity. Because gravity is a relatively weak force, it takes billions of years to pull scattered matter across the expanding void into large, organized structures. Webb found the Webb Quintet, a group of 5 fully formed galaxies caught in a gravitational collision just 800 million years after the Big Bang. Advanced data mapping revealed that these 5 structures are physically connected by vast bridges of gas spanning hundreds of thousands of light years. Hiding within these bridges is a massive abundance of ionized oxygen. This heavy element is forged only inside dying stars, and it exists here in quantities that the established timeline of star formation cannot yet account for. Gravity did not have enough time to organize this much matter into a collision, and early stars had no time to produce this much oxygen. The schedule for how the universe built itself is out of sync with our observations. If expansion, stars, black holes, and gravity are all behaving in ways the Standard Model didn't predict, does that mean our core equations are dead? Not quite. The model still explains 14 billion years of other cosmic behavior with incredible accuracy, from the clustering of modern galaxies to the chemical makeup of the early universe. We are in a position where new, high-precision data is being integrated into a functional map, but the fit is creating pressure on the rest of the model. It suggests that while the map is correct in many places, it is missing a critical set of variables. One potential missing variable is a phenomenon called early dark energy. Scientists are looking for evidence of it in the first few 100,000 years after the Big Bang, a stretch of time we have never directly observed. A sudden, temporary burst of expansion in that early era would send a ripple forward through 14 billion years. This kick would change the starting conditions just enough to elevate the modern expansion rate, potentially reconciling Webb's findings with our existing equations. We are living through the moment our map of reality reaches its current limit. The universe isn't broken, our understanding of it is simply growing. As Webb pushes further into the dark, the next version of our cosmic history will be stranger and more detailed than anything we've imagined.